we're going to shift gears a little bit and talk about type 1 and type 2 error. And then we're going to see why we introduce this concept now after multiple comparisons in ANOVA. Remember, statistics is backwards. The way we play this game is you state a null hypothesis. After you've set some alpha level of the criterion for where you're going to say is weird or what is going to be statistically significant, you go out and you get some data, summarize it with the test statistic, turn it into a p-value, and say what's the probability of observing that test statistic if the null hypothesis is true. And if it's less than alpha, you reject. If it's greater than alpha, you accept. No, you don't accept. You fail to reject. This is the game, all right? These are the rules. You know this. We've seen this again and again. We saw it with one sample t-test, independent sample t-test, paired t-test. We saw it with regression slopes. We saw it with ANOVA and so on. This is the game, right? It's kind of like this. The null hypothesis is usually not what we're interested in. We're actually usually interested in the alternative hypothesis. Nobody goes out and invents a drug so that they can sort of show that the drug is no better than a placebo. But when you do the statistical test, you first assume that nothing is going on. You're setting up this sort of straw man. You actually think that something is going on. Usually you start with the alternative hypothesis. You start, this is an old TV commercial for a erectile dysfunction drug. Someone invents the drug and says, let's assume it doesn't work. And then we'll go ahead and collect some data and say, what's the probability of getting that data if it didn't work? That probability is pretty small. P is less than 0.05. So maybe our assumption that it didn't work is wrong. Now, an interesting analogy to this is the justice system. In this country, at the time of this writing and recording in 2020, we have this thing called innocent until proven guilty. So even if you committed a crime and everybody knows it, when you walk into the courtroom, the first thing that people say is, hey, let's assume this person is innocent. And then we'll go out and collect some data and see if we can reject the presumption of innocence, right? So we usually go in, we want to try to convict somebody of a crime. We want to try to prove that things are different, that there's something there, because it takes work and time and effort. But in order to do that, we first have to set up the null hypothesis, that nothing is going on. And one thing that's really important, and we saw this, remember that stupid example we had with the fictional NKE enzyme and the weightlifters? We said one thing we're really going to need is some sort of standard of judgment. What is weird enough or strong enough or convincing enough to reject the null hypothesis? In the statistics point of view, I say, what sort of data would be so extreme that it would be unlikely to due to chance alone, and there must be something other than chance that's playing a role, such as this drug works? In the courtroom, we say innocent until proven guilty, but how much evidence do I need to reject that presumption of innocence? In statistic, we've seen most of the time people jump to this arbitrary alpha level of 0.05. But there's nothing magical about 0.05. In the courtroom, there's actually two, maybe even more than two, different standards of evidence. In a criminal trial, in order to convict somebody, you need to have proof beyond a reasonable doubt. That's a lot of evidence. That is a lot of evidence, and you might not be able to gather that much evidence. In a civil trial, the standard of evidence is not as high or strict. You need what's a preponderance of evidence. Now, I'm not a lawyer. I do play one on TV, but these are different standards, and one of them is tighter than the other. And we're going to see that we might want to think about why we're choosing 0.05 and why we use it. And now we're going to see why we do this in the context of ANOVA. Now, what happens in the courtrooms is, sadly, and what happens in Stata is that, as my kids say, nobody's nerfect. Sometimes you screw up. Now, if the world were perfect, every time you had an innocent person, the process would play out, and the verdict would be no, not enough evidence to convict. And good, did a good job, right? Somebody had been wrongfully accused, and the system worked, right? Now, also, if the world were perfect and you had somebody who was guilty, the verdict would be guilty. And what would this be called? Justice has been served, right? That is ideally what would happen if things were great. The analogy to statistics is, say, the null is false. In other words, my drug works. My drug works. And you do the study, P is less than 0.05. Good job. Something was out there and you found it. Okay. The other thing is my drug doesn't work. In other words, the null is true. The mean of drug is equal to the mean of placebo. And if that's the truth, right, your drug doesn't work, you would get a p-value greater than 0.05. That is when things work perfectly. I'm going to erase all this stuff here. Erase you. Okay. Now, sometimes mistakes are made. What if you have an innocent person who is convicted? In statistics, we call this a type 1 error. The null is true. In other words, there's nothing going on in the real world, but the process is such that you go around saying, hey, I found a significant difference. This is what is known as a type 1 error. It's equivalent roughly of convicting an innocent person. Type 1 error. That's not good, convicting an innocent person. Sometimes someone is guilty. There's something going on. Something happened, but you don't have enough evidence. So you let that guilty person go. Now, you don't actually know whether this person is guilty or not. Maybe they know. Maybe God knows. She's busy. She's not going to get involved in other people's problems. It takes 3 people to have a good fight, and God stay out of it. This is known as a type 2 error, letting a guilty person go free. That's not good either. In statistics, this is what's known as a type 2 error. The null hypothesis is false. The drug works, but you get a p-value greater than 0.05. So these things are not good. Convicting an innocent man, letting a guilty man go free. Those aren't good, but it happens. And we're going to see in statistics, it happens in a way that we can quantify and that we can control it. What's worse, though, convicting an innocent man or letting a guilty man go free? This is some quote from the Salem witch trials. It's better that 10 suspected witches should escape than that one innocent person should be condemned. This is from an old neighborhood up near Tufts in Chinatown in Boston. Ben Franklin, the best president we've had, he made it on the $100 bill. It's better that 100 guilty persons should escape than that one innocent person should suffer. Where is this line? This is another building up by Tufts. This is a copy shop, which doesn't exist. It's on Milk Street, I believe. It's where Ben Franklin used to live. Not when it was a copy shop. Where is the line between convicting innocent people and letting guilty people go free? Well, we're going to see. You get to decide this. The type 1 error is when you reject a null when it is actually true. Kind of think of it as a false positive. A type 2 error is when you fail to reject a null when it actually is not true. There's a difference out there and you failed to detect it. And we'll think about this in a second. So, type 1 error is the rejection of a true null hypothesis. Here. And I want to ask you this. How often do you think that will occur? Pause the video. Think about that for a minute. How often If there's nothing out there, if the null is true, if the mean of men is equal to the mean of women, that's the truth, and you run a study, how often will you commit a type 1 error? What did you say? It's interesting. Let me walk you through the thought process of how often would I commit a type 1 error. This is a distribution of t statistics. And again, this would work for an F statistic or the statistic for a slope or anything. If the null is true, what would you expect to see? If the null is true, you would expect to see a t around 0. It would bounce around randomly. That's called the standard error, the statistic. And if the null were true, sometimes you would just sort of randomly get stuff out in the tails. Sometimes. If the null is true, if there's nothing going on, sometimes you will get results in this shaded in area over here. What percent of the time will you get results in this shaded area? Well, what is that shaded area? On this graph, it looks like it's about 5% of the time. So in other words, that shaded area, if we're doing a 95% CI, that's our alpha. So if the null is true, you will get results in these tails, whatever those tails are, alpha percent of the time. Whoa, wait a second. If I get results in those areas, then my P is less than alpha. And when my P is less than alpha, what do? I run around saying, hey, statistical significance, look at me, look what I found. Something's out there. And what percentage of the time will you do this if the null is true? 5% of the time, you will find something. If nothing is going on, think of the dumbest research question you can think of, where there's definitely nothing going on. If you test that, there's a 5% chance that you will declare statistical significance. This is a bit of a mind bender for students, but it's the rules of the game. It's how we set up the rules of the game. 5% of the time, if that's our cutoff for weirdness, then 5% of the time we'll declare something when nothing exists. Now, how does that tie into this idea of ANOVA? Why are we doing this now? I went camping once with my friend Kevin. And Kevin and I, we were driving up to Maine. And when we got up to Maine, it had started to rain, thunder, lightning, horrible weather, completely ominous. And this was real camping. This isn't the camping where you take your SUV and you open it up and then it's not glamping. This was like we were going to park the car. We were going to be at a trailhead, walk, go across this giant meadow, carry all of our stuff with us, set up tent, just me and Kevin. And we're getting there, and Kevin's getting nervous. He doesn't like this idea of having to be out in the lightning, especially trying to cross this open field. And I try to assuage Kevin's fears, like, Kevin, listen, dude, if we cross this field, there's a chance we're going to get struck by lightning. And Kevin says, what's the chance? And I say, maybe a 5% chance. And Kevin says, oh, okay, that's worth it. That's worth taking that risk of getting struck by lightning, a 5% chance. So we're starting to cross the field. Kevin says, did you bring the beer? I brought Narragansett, the beer of the clam, the famous beer from Rhode Island. Kevin never had this before. And Kevin asked me a really interesting question. He said, Tibor, I've never had that beer before. Is it a twist off? Why? I want to know if we need to bring a bottle opener. Because if we go all the way across that field and we try to open this beer and we don't have a bottle opener, we got to come all the way back across that field. And every time we cross the field, there's a 5% chance we're going to get struck by lightning. It's very interesting. If you keep crossing that field, there's a 5% chance you will get struck by lightning. Eventually, you're going to get struck. When? You don't know. So, if the null is true, there's a 5% chance you're going to end up in one of these tails. Get struck by lightning. I almost said strike lightning. Okay, we're fine with that. That's the rules of the game. We're okay with that. If we weren't okay with that, we would change alpha. We would make it smaller or tighter. But the thing is, sometimes we do a lot of statistical tests. And if you do a lot of statistical tests when nothing is there, eventually you will get struck by lightning. When? You don't know. You don't know. This is known as the multiplicity problem. If null is true, in other words, if nothing's going on, 5% of the time, technically alpha percent of the time, you will declare a difference. So sort of every time we run a test, every time we cross that field, there's a chance that we're going to find significant results, even when no real difference exists. I want to show you a couple simulations from Jerry DeLaw's Little Handbook of Statistical Practice that will drive this home. So I'm accessing this site. It's 2020, and this is DeLaw's Little Handbook of Statistical Practice. And he's got this great little set of readings down here. After y is 0.05, which we've discussed, he says, all right, let's do this little lesson that we have. And he set up this little simulation, which is really cool. Each of these boxes, there's 100 of them, have behind it basically a coin flip, but the coin is set so that 95% of the time it says not significant, and 5% of the time it says significant, like exclamation point, significant. And it's simulating in a way, if you went and did 100 of the stupidest studies you could think of on things where there was no effect or nothing out there, sometimes you are going to find a p-value of less than 0.05. 5% of the time you're going to find that. So I'm going to press this test button and run 100 tests, and there you go. Now this is really interesting. This first column here sort of shows you not significant, not significant. Okay. But if you look at the second column, significant. Something pops up. You find something. And sort of tongue-in-cheek, publish, in all caps, exclamation point. So when you run a bunch of tests, you will find something. You will find something. I want to show you a cool comic from XKCD. XKCD is a great comic by Randall Munroe, and he does a great job of poking fun at the way we do science. Jelly beans cause acne. Scientists investigate. We found no link between jelly beans and acne. P is greater than 0.05. But if we look at different color jelly beans, and here he goes through, there's no link between purple and brown and pink, greater than 0.05, greater than 0.05, greater. That's going down that first column of that thing that we just saw. Guess what? Eventually you're going to find, if you test enough colors, boom, 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 green. 95% confidence. And then this really poorly written thing. Only 5% chance of coincidence. The 5% chance of making a false positive is true if you just run one test. And we're okay as science, capital S, science, of accepting that risk. But they didn't only test one color. They test color after color after color. I'll show you. DeLaw also simulated this. What color jelly beans cause acne? What color jelly beans cause or prevents acne? I'll hit the test button. Oh, good. Justice has been served. Wrongfully accused jelly beans. Test again. Oh, wow. Here we go. So now we have two significant results. What do? How do you write this up? It'd be great if you were upfront and said, you know what? We really didn't have a specific hypothesis going into this. We tested a ton of different colors, and these two have come up. Now, sadly, what you often see is that people will say, pink jelly beans cause acne, publish. Pink and yellow cause acne. And then this idea of like, well, how do we explain that? And we're really, really good as creatures coming up with post hoc explanations for things that we've seen. Anytime you read the newspaper, you'll see a headline like, hey, the economy went down yesterday because of blank, blank, blank. If you really knew that's why the economy went, wouldn't you have written that paper story yesterday and told me that that was going to happen? No. Some people argue that all that our brain is actually a constant post hoc story that's made up in real time to explain what's going on. I'll show you a little bit about the ability to tell stories when we ask a separate question. What type of cancer is caused by cell phone usage? Let's imagine the same thing. Cell phone is not related to cancer, but if I test a bunch, I get this: colon cancer and breast cancer. If you got that, now you get to make up a story. Now you get to make up a story. And look, this is completely random, that these two things came up. But I mean, I can come up with a story that, I mean, breast cancer is obvious because I keep my phone right here. And colon cancer is obvious because I put my phone in my back pocket. Sounds like a pretty good story, doesn't it? P is less than 0.05. P is less than 0.05. I got those numbers completely randomly. I could have gotten this: skin cancer and ovarian cancer. I mean, ovarian cancer, that's obvious because you keep your phone in your pocket right here. And melanoma, I mean, your phone's just against your skin. So you have to be careful of the post hoc explanation. Let's look back at these slides. When did you make a type 1 error? You never know. You never actually know if the null hypothesis is true or not. You can be a little skeptical of some results. If you test a ton of things, you're going to find something significant. And I think you should frame and report that appropriately and say, hey, guys, we tested a ton of different things. We found that it's all about the yellow and the pink jelly beans. And then you get to write the words that you see at the end of so many studies. More research is needed. My goal in life is to write one paper where it ends: no more research is needed. As of this time of this recording in 2020, it hasn't happened yet. So these are some situations where you should be skeptical. And we'll look at a few examples of what I think might be potential type 1 errors.